discuss to you about linear programming, ways to solve it, and examples for you to better understand.
I'll give you the floor to Kim to have a short introduction about linear programming.
What is linear programming? Linear problems in general are concerned with the use or allocation of scarce resources like labor, materials, and capital in the best possible manner so that the costs are minimized or profits are maximized. We use linear programming in order to find the optimal solution. There are different methods in order to find the optimal LB solution. One of those methods are graphical and simplex methods. In this video,
First example, an airline offers coach and first class tickets. For the airline to be profitable, it must sell a minimum of 25 first class tickets and a minimum of 40 coach tickets. The company makes a profit of $225 for each coach ticket and $200 for each first class ticket. At most, the plane has a capacity of 150 travelers. How many of each ticket should be sold in order to maximize profits?
So let X be number of coach tickets, Y be number of first class tickets. Next, we need to identify the objective function. Since the goal is to maximize profits, our objective is identified. Maximize profit P is equals to $225 X plus $200 Y. After identifying our objective function, we then determine the constraints. In this case, we have the following constraints. Constraint 1. At least 25 first-class tickets. This means that 25 or more tickets should be sold. Constraint 2. At least 40 coach tickets means that 40 or more tickets should be sold. Constraint 3. Sum of coach and first class tickets should the Constraint 3. Sum of coach and first class ticket should be 150 or fewer. And lastly, Constraint 4. Non-negativity constraints. This means that values of X and Y should be positive. Now that we have known our objective function along with our constraints, we can now plot each inequalities. In order for us to find our optimal solution, we must know our corner points. Our corner points can be found at our feasible region, since corner points falls along the feasible region area. We then have the following points, point A, point B, and point C. In finding the values of these points, we will solve it using algebraic method. Then we were able to know the points. Point A has 40 and 110, point B has 40 and 25, and point C has 125 and 25. To verify the winner, we must see which of these points maximizes the objective function. Substitute the following points of A, B, and C to our objective function's equation. Then identify which points maximizes profit. In this case, point C maximizes profit. Therefore, the airline should sell 125 coach tickets and 25 first-class tickets.
Here, a health food business would like to create a high-potassium blend of dry fruit in form of a box of 10 fruit bars. It decided to use dried apricots which have 407 milligrams of potassium per serving and dried dates which have 271 milligrams of potassium per serving. A company can purchase its fruit in bulk for a reasonable price. Dried apricot costs $9.99 per pound for about 3 servings, and dried dates cost $7.99 $7.99 per pound for about 4 servings. The company would like the box of bars to have at least the recommended daily potassium intake of about 4,700 milligram, but would like to keep it under twice the recommended daily intake in order to minimize cost. How many servings of each dried food should go into the box of bars?
So we begin by defining the variables. We let x equal to the number of servings of dried apricots and y equal to the number of servings of dried dates. We next work on the objective function. For apricots, there are 3 servings in 1 pound. This means that the cost per serving is $9.99 divided by 3, so we have $3.33. The cost for x servings would thus be 3.33x. For dates, there are 4 servings per pound. This means that the cost per servings is $7.99 divided by 4, so it would be $2. The cost for y servings would thus be 2y. So we now have the minimization problem of the objective function z is equal to 3.33x plus 2y. So after getting the objective function, we now solve for or work on our constraint. So it is given that product must contain at least 4,700 milligram of potassium, and product should contain no more than 4,700 times 2. So we have 9,400 milligram of potassium. Thus we have our constraints 407x plus 271y is greater than or equal to 4,700, and 407x plus 271y is lesser than or equal to 9,400. And of course, our non-negativity constraint, x and y is greater than or equal to 0. After that, we need to graph this equation or our constraint. So we need to solve the value of x and y. So for the first constraint, in solving for y, we need to let x is equal to 0. So 407x plus 271y is equal to 4,700. So we have 0 plus 271y is equal to 4,700. So divide both sides by 271. So we have y is equal to 17.3. So point lies on 0 and 17.3. And in solving for x, we let y is equal to 0. So 407x plus 271y is equal to 4,700. 407x plus 0 is equal to 4,700. Divide both sides by 407. So we have x is equal to 11.5. So point lies on 11.5 and 0. And for the second equation, in solving for y, we let x is equal to 0. So 407x plus 271y is equal to 9,400. 0 plus 271y is equal to 9,400. Divide both sides by 271. So we have y is equal to 34.7. So point lies on 0 and 34.7. And same goes with solving for x. So we let y is equal to 0. 407x plus 271y is equal to 9,400. We have x is equal to 23.1. So point lies on 23.1 and 0. So we plot this in our Cartesian plane. So since the problem is bounded, we now check to see which one minimizes cost. So for 0 and 17.3, we substitute this to the objective function. We have 33.3 times 0 plus 2.2 times 17.3 is equal to 34.60. So for 0 and 34.7, we have 69.40, and 11.5 and 0, we have 38.30, and 23.1 and 0, we have 76.92. So our optimal solution